Hello, good evening to all the participants. Hello, can the participants hear me?
Yes, sir. We
Yes,
can hear you.
good evening to all of you.
Good evening.
Yes, so okay, so at the outset, I would like to wish happy Ganesh Chaturthi for all of us who are celebrating this festival, and we will start the session. So I would like to ask one of the participants, like Mr. Subhash. You have been attending all the live interaction sessions and participating very actively in the question answer. So I would like to not to put you on spotlight or anything, but I would like to just know how the experience has been so far. With what expectations you took the course, and how you have been able to use this the lessons, because this NPTEL course, it is it's a work in progress, and we want to make it relevant for the upcoming in the future also. So if you'd like to take a few minutes and discuss.
Thank you so much, sir. So, before joining this NPTEL course, my
Yes,
expectation was to learn about the behavior of RC structures.
right,
So, currently, I am practicing civil engineering in Japan,
right,
and
right,
here we have to design the buildings not only for the forces, but yeah, it's earthquake is quite significant, so we have to deal with this type of extra forces. So
right, right.
it is, I think, it is quite important to learn about the behaviors and how the structure performs when load is subjected upon them.
Yes,
So this course is quite helping us to understand. So far we have learned about the design of beams in Flexure.
yes,
So we have understand quite deep about how the structure performs when certain loads are acted upon it. So uh, after this, we are looking forward to learn about the design of columns and other structural components.
yeah, yeah,
We are really grateful that NPTEL has created such a beautiful course, and
hello, yeah,
so sorry, sir.
yes,
So I am learning this course by this interactive session has also been incredibly helpful for understanding the concepts that sir has taught on the video lectures.
yeah,
So
yeah,
thank you so much, sir. And this is
yeah.
what I have to say.
So I think the participants can register for the exam. So is it possible for you? But I think in as per my knowledge, I think only there are exam centers only within India. So I'm not
Yes,
aware.
sir. I am from Nepal.
Yeah.
So currently I am in Japan, but this October I am coming to Nepal. So
Okay.
during that time, I will be visiting India and take exam. I have registered.
Okay.
So me and my wife, we have both registered for the exams.
Okay, okay. Yeah, so yeah, thank you. That's very nice to know. Because like even I am working as a TA for a NPTEL course for the first time. So I wanted to know, understand the learning experience so that moving forward we can make it more useful, so that we can help in the knowledge dissemination for the design and construction of RC structures.
Yes.
Yeah, so your feedback is very important, because one of the most important aspects for the progress of any country is there has to be a synergy between the industry and the academia. So it has to go hand in hand, and we will try to address as much as possible, so that maximum participants can benefit from this, and our course on this advanced reinforced concrete structures, it will be useful for the participants. And
Thank you so much,
yeah,
sir.
yeah,
And so sorry to disturb you.
yes,
So,
please.
as me and my wife, we are both registered for the exams. We are
Yes,
currently joining from the same account, but so she has also some feedbacks to say. So, please.
Good evening, sir.
yes,
I,
good
I
evening,
have
sir.
also I have also been joining the live session together with Subhas, and we have also currently designed one complex structure.
Okay, that's great.
Yeah, structural design of the complex buildings, and by learning this course, we are also cross-checking everything we have designed, like how our building would have responded, like beams and everything. So it has been quite helpful for us to deep understand the behaviors of all the beams, and now we are also like confident that we have designed in right way, and we can also use it in the future while designing for other buildings. So it has been quite helpful, and we are enjoying the course. Thank you so much.
Yeah, right. Thank you for such kind words. And again, I hope that we can put the knowledge that we are gaining to good use in our practice. Because ultimately, I think as engineers, we should be able to apply the knowledge that we learn in the classrooms and in these discussions in our practice, so
Yes.
that we can be part of building you know good infrastructure, disaster resilient infrastructure.
Yes.
Yes,
uh,
sir.
yeah, so thank you for the feedback. We will
Thank you.
start, yeah, we will start the discussion shortly.
Okay.
Okay, sir.
So as I was discussing, this course, it is advanced reinforced concrete structures, and it is essentially in the UG course we study about the design, but I think here, as we are studying the advanced aspects, we go into the details. We understand the behavior of structures, right from the level of understanding the forces, the stresses. uh, yeah, so I think with more and more constructive feedback as yourself provided, and with encouragement, we can make really good advances in this endeavor of ours, I believe.
Thank
Yeah,
Thank you, sir.
yeah, thank you. So on that note, I think it is time, we can start with the session. Yes. So yes, I hope that my screen is visible now.
Yes, sir. It's visible.
Okay, okay. Okay, so welcome to the week 7 of the live interaction session. This course is brought to you by NPTEL, and the title of the course is Advanced Reinforced Concrete Design. and the course instructor is Professor Surya Prakash from IIT Hyderabad, and today we are going to start the live interaction session 7, and presently we are dealing with the flexural members. So this is the third part of this fifth module, and this interaction session is being presented by me. My name is S. Lalit Sagar. I am a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi. So we are going to follow this similar protocol. Firstly, we are going to look into the lecture slides. We are going to summarize what we taught, what we learned in this week, and after that I have prepared certain multiple choice questions, combination of the theoretical and the numerical aspects, and we can discuss with them. So first, without any further delay, let us start with the summary. So presently we are in the module 5, that is behavior and design under Flexure, and this is you can say it's the fifth part of this module 5, that is the flexural design aspects using IS code. So we dealt with certain aspects such as the behavior of flexural members, considering the material properties earlier on. So now we are delving into the aspect of design. So whenever we talk about design, we need to introduce certain factors of safety when it comes to the material properties or when it comes to the loading. So when it comes to the material properties, we are going to consider certain partial safety factor for the material in terms of the maximum stress that it can attain. So we are going to be delving into the design aspect in today's live interaction session. So as we saw in the last week and last to last week, we are going to be dealing with both the singly reinforced section and the doubly reinforced section, and then we are going to be looking into the aspects of the flange section also, which is quite useful in the design. So some of the assumptions, few of them we might have already considered in the earlier parts of the module. However, I would like to reiterate them for the sake of completeness. So the plane sections that are normal to the axis, to the longitudinal axis of the flexural members, they remain plane after bending also. They remain plane prior to the bending, and they are considered to remain plane even after the bending. And the maximum strain in concrete at the outermost compression fiber is considered to be 0.0035, and this is the acceptable stress strain curve is rectangular parabolic, as we will be looking into at the later stage. And for design purposes, the compressive strength shall be assumed as 0.67 times the characteristic strength. So what is the characteristic strength? That is FCK. And in addition to this reduction of the characteristic strength, we are going to apply a partial safety factor. So 0.67 divided by 1.5, so that turns out to be approximately 0.45 times the characteristic strength. So that we are going to be looking at the stress block parameters in detail in the upcoming slides. Then the tensile strength of concrete is being ignored. Okay, and pardon me, I'll get back to the lecture. And this partial safety factor is with respect to concrete, and this partial safety factor, that is 1.15, is with respect to steel, because of the simple reason that while concrete is being casted in the site conditions, the reinforcing steel is being fabricated in factories in a controlled environment, and the maximum strain in tension reinforcement is considered as Fy by 1.15 ES 0.002. and this 0.002 is because we considered 0.2% proof strain. We are going to consider the offset method in order to determine the maximum strain, which is why this factor comes along. And these are the stress block parameters. So when we were considering the material properties, we considered
Excuse me, sir.
yes,
Sir,
yes,
your
please.
screen is not visible.
Oh, okay, okay. Yeah, thanks for.
Screen is visible, but it's so now it's visible.
Now it is visible. Okay, okay.
Yeah, yeah.
Yeah, please interrupt me. Whenever there is there is any issue, please let me know. Right. So in the previous parts of the module, we saw that the stress distribution within concrete, it can be of different shape. It can be rectangular, but for the purpose of the design as per IS code, we are going to be considering this partially rectangular and partially parabolic stress distribution. So actually this corresponds to the point of zero strain, and as in when the strain increases, we can expect that the stress along the depth of the cross section to vary in this manner. So when we for the sake of simplicity, we are going to consider that the average stress is 0.36 FCK, and the resultant, the point at which resultant acts is at a point of is at a distance of 0.42 XU, where XU is the depth of the neutral axis, and the peak stress at this point, that is 0.45 times FCK. Okay, so this corresponds to the resultant compressive force in the concrete block, and this corresponds to the material properties of or the stress strain characteristics of reinforcing steel. Up to a stress level of 0.8 FYD, it will vary linearly, and there is no reduction in the stress as such. But beyond the point of 0.8 FYD, where FYD corresponds to 0.87 FY, we are going to reduce it by a factor of 0.87. So 0.87 times FY. So this we are going to be using in our analysis as well as the design also, and we are going to be looking at it. Actually, this is taken from the design aids to the reinforced concrete structures, that is SP6 SP6 1980. So we are going to look at this stress strain table in the numerical examples also today that we are going to discuss. Moving on, there is a way of this XU max by D. XU max is the limiting depth of the neutral axis, and D is the effective depth. So this depends on the grade of steel, and yeah, so corresponding to 250 grade, 415 and 500, the XU by D varies. When you plug the value of Fy over here, we get different values of XU max by D, and yes, again our we intend to design under reinforced section because it leads to a tension control failure, okay, as we have discussed in the previous parts of the module. Moving on, again when corresponding to limiting neutral axis depth, that is XU max, we have the moment of resistance, that is mu limiting, that is the ultimate limiting moment of resistance. So that is given by the compressive force, the resultant compressive force by the lever arm, okay, that is 0.36 FCK B into XU max into D minus 0.42 XU max. And when you normalize that with respect to FCK BD square, we get this variable K, okay. And then further we have a limiting percentage of steel reinforcement, and that varies corresponding to the grade of steel. So for 250 we have 0.22 times PTLM over 100 into Fi by FCK. We are going to be dealing with this limiting reinforcing steel area in the upcoming numericals. And this is the moment of resistance considering the tensile force. In the earlier, in order to develop the expression for the limiting moment of resistance, we considered the resultant compressive force. In this case, we are going to consider the tensile force within reinforcing steel, and this we can find it in the Annex G of IS 456 also. So we can take the help of the annexures in order to help in our analysis and design calculations. And we have looked into two methods of determining the area of steel required. Area of steel, whether it is an under reinforced section or it is an whether it is a singly reinforced section or a doubly reinforced section. So we have looked at essentially two methods. So the method one involves the calculation of neutral axis and then determining the area of steel from the value of xu by d, and the second one is a direct calculation where we are going to find out the value of r, that is mu by bd square, and then we are going to determine the pt, that is percentage of reinforcing steel, followed by the area of reinforcing steel. And then we looked into certain examples. I will not go into the details because we will be dealing with the numericals in some time. And then we compared what is the ultimate moment of resistance of the IS code obtained values with the actual material properties that we have looked into in the previous modules. So definitely, when we consider the IS code, we will have to bring in certain partial safety factor, as a result of which the ultimate moment of resistance and curvature, it will be lesser for the design codes because they are more conservative. We are going to be looking into those aspects as well in today's interaction session. And here we have discussed the doubly reinforced cross section, why we need to, what are the scenarios in which we need to provide the compression steel in addition to the steel in the tension region, and some of the additional benefits such as increased ductility and change in the failure mode to a tension governing failure mode. And yes, how to perform the calculations in order to obtain the area of reinforcing tension steel that is required. And then we have looked into certain numericals. Okay, and we have done certain analysis also, finding out the moment of resistance, ultimate moment of resistance, and comparing with the actual material properties. Again, we can see that the moment of resistance and the curvature obtained using the IS code is generally a percentage of the values obtained from the actual material properties because of the partial safety factors. Then ultimately we looked into the analysis of flange section, such as the inverted, such as the T beams and the L beam. So we have dealt with the T section essentially. We have looked into the aspects of effective flange width, and how you consider the flange width as per the IS code, and how you can you can idealize various shapes of the beams. The twin T can be idealized into a single T section, and the box section can be idealized as an equivalent I section. and then how the stress analysis is considered for a T section, and how to calculate the ultimate moment of resistance. So this was the summary of the module on the flexural members, and yeah, in the next module we are going to be dealing with the shear. So on that note, I think we can start with today's question and answers. Yeah, so yes, let us start with the question and answers. So yes, question number 1, according to IS 456, in the design for limit state of collapse in flexure, what is the area of stress block for concrete in compression? Further, what is the depth of resultant compressive force from the extreme compression fiber? Okay, yeah, please take a minute and answer the question. Hello? 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 Hello?
Yes, sir.
Hello.
It's
Yeah, yeah,
yes, sir. Yeah, it's audible now.
yeah. Sorry, I was, giving a summary of the lecture. I don't know when, I lost the connection. Hello.
Yes, sir. It's you were at the
So, how long was I away from the call?
it's a bit minute ago, sir.
Oh, okay,
About a minute ago.
okay, okay. So, I think you saw the first question.
No, not sir. The
Okay,
question was not visual.
right,
We were
right.
in the lectures part.
Yeah, 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 yeah. So, yeah. Sorry for the interruption. We will start with the questions.
Okay, okay,
Yeah,
sir.
yeah, yeah. So this is the question. Yeah, kindly take a minute and let me know the answer.
So your screen is not visible.
Oh, I'm sorry. I'm sorry. I forgot. Oh, yes. I hope my screen is visible.
Yes, sir.
Yeah, please go ahead.
Answer D.
Okay. Thanks for your response. And yeah, since we don't have other participants, I think we can, yeah, just go ahead. And answer D is absolutely right. And yeah, so what we see here is essentially um, it has been taken from the IS 456 2000. So if this is the characteristic strength, so we apply a partial safety factor of 0.65. So how do we get this? 0.67 is obtained from 0.8 into 0.85, as you might remember from the previous lectures. So 0.8 is to convert from the cube strength to the cylinder strength, and this 0.85 is to account for the size effects. And once you divide this by partial safety factor for concrete, which is 1.5, we get a value of 0.45 FCK. So it is 0.45 FCK for this particular region, and there is a parabolic variation along this. So this one, it is going to be constant for a distance of 3 by 7 times xu, or 0.42 xu, right? So when you consider this entire stress stress block, so the average stress comes out to be average stress comes out to be 0.36 FCK, and this is the extreme compression fiber, right? So basically, when you consider a beam which is bending about the neutral axis, So this is the point corresponding to 0 strain. So essentially, this is rotated. What we get here when we rotate it, 90 degrees, 90 degrees in the anti-clockwise direction, we get this this stress block that we are seeing here. Okay, yeah. So as I was mentioning, this would be average stress would be 0.36 FCK multiplied by the depth of the neutral axis. So this would be XU, right? And this essentially acts at a distance of 3/7 or 0.42 times XU. Okay, so we'll be using this in the upcoming questions. So yeah, option D is the right answer. Moving on, for a reinforced concrete cross section, the ratio of limiting depth of neutral axis to the effective depth depends on which of the following factors?
Answer B, grade of reinforcing steel.
Yeah, okay, thank you for the response. Yeah, option D is, it is the correct answer, because as we were seeing, essentially we are interested in finding out this particular value, the ratio of the limiting depth of neutral axis to the effective depth. So when you consider similar triangles, you have this strain value 0.0035 divided by XU max is equal to the strain in reinforcing steel divided by this value, which is D minus XU max. Yeah, so when you after some when you work out the ratio of XU max divided by D, we get this expression, and we know that the value of Young's modulus of steel, it is same for different grades of steel irrespective of whether it is 250, 415 or 500. So when we plug the value of Fy, we obtain different values of XU max by D, and yeah, so for different values of for different values of Fy, we obtain different values of XU max by D. So essentially this term XU max by D, it is a function of only Fy. Okay, so so option D, that is grade of reinforcing steel, is the right answer. So we move to question number 3. When the grade of reinforcing steel increases, what happens to the ratio of neutral axis to the effective depth, that is XU by D?
Answer B, decreases.
Okay, thanks for the response. Yes, so option B is indeed the right answer. So yeah, as we saw in the previous slide, we are looking at essentially the same slide from the lecture, and as you in this particular expression, as the value of Fy as the value of Fy increases, the value of xu max by d, it decreases because Fy is in the denominator, and essentially the concept which explains this is that if you consider reinforcing steel, we have reinforcing steel over here right? So if you take Fe 250 grade, Fy is equal to 250 and Fy is equal to 500 MPa. Okay, so here essentially it takes lesser area in comparison to this Fy 250 in order to achieve a similar tension steel, tensile force. Okay, as a result of which whenever the grade of steel is lesser, you need to activate a higher depth of the xu max in order to obtain equilibrium between Cc and Ts. Okay, Cc and Ts. So whenever we are using steel of lesser grade, we need to activate a higher value of xu max. Okay, which is why the value of xu max by d is slightly higher when compared to Fy is equal to 500. But when when we are using Fy 500 MPa steel, so the area of concrete that is activated in order to develop this resultant compressive force, that is lesser when compared to that we get when we use Fy is equal to 250 MPa steel, as a result of which, as when you increase the grade of steel, when you increase the grade of steel, the value of xu max by d decreases. Okay, so that is the concept behind this the question. So yeah, option B is the right answer. Okay, moving on, let's go to question number 4. According to IS 456/2000, a beam is designed as which type of failure of the which type of cross section, and what is the corresponding mode of failure?
Answer F.
Okay. Okay. Thank you for the response. And as you mentioned, our option is it's absolutely correct. We have seen in the previous parts of this module also. So again, when we consider reinforced concrete beam, so we want to ensure that it is under reinforced cross section, because if it is under reinforced, then it is primarily governed by the yielding of steel. So whenever it is tension controlled, it is undergoes significant elongation when compared to the strain within concrete. So that gives us lot of warning and time before the failure. And in contrast to what happens in a tension control failure, in a compression control failure, the concrete pretty much fails suddenly without giving any sufficient warning. So it is always desirable to achieve an under reinforced cross section, so that the resulting failure mode would be the tension controlled. So which is why this ultimate moment of resistance, it corresponds to a balanced cross section. So we always make sure that the factored moment, it is less than this xu max. So if the demand is greater than the xu max, if the demand is greater than XU max, I'm sorry, it is greater than, pardon me, let me so when the demand is greater than the limiting moment of resistance, that is mu lim, for a singly reinforced cross section, we go for a doubly reinforced cross section. Okay, so yes, so whenever we are designing as per the IS code, and for most of the buildings codes across the world, we want to design the beam as an under reinforced cross section, and the failure should be governed by the tensile failure of the reinforcing steel. Okay, moving on, in the analysis and design of beam for flexure, what does the term R represent?
Answer A.
Yeah, answer is absolutely right. So this is not a standard notation, but for the ease of design, and for the design using the SP6 and the design aids, we are going to use this term a lot. So I just wanted to start with the basics. Yes, as we can see, R is given by mu divided by BD square. Okay, this is going to help in the simplification of our calculations. So moving on, we start with the numericals now. Consider a beam having a width of 250 mm and overall depth of 450 mm. The concrete has a characteristic strength of 30 MPa, and the beam is reinforced with 4 bars of 20 mm diameter. Fy is equal to 500 MPa on the tension side. Assuming moderate environmental condition and 10 mm stirrups, or the transverse reinforcement, what is the depth of neutral axis as per IS 456-2000 without considering the limiting depth? Okay, kindly take 1 minute to answer this question. So this is a pretty straightforward calculation. We just need to equate the compressive force with the tensile force that has been developed in the beam, and we need to determine the value of XU. So do the participants have the answer? Am I audible to the participants?
Yes, sir.
Okay, okay. So I think we can go ahead with the answer. Okay, so the correct answer was option C. So let us look at, it is quite straightforward, but it's a little tricky. We can look at the solution, then we can discuss. Right. So as per the Annex G, Annex G of IS 456. Pardon me for the poor handwriting. We need to find out the value of xu. So we have xu by d is equal to point. I'm sorry. We have 0.87 Fy AST divided by 0.36 FCK into B into D, right? So essentially what we are doing here is we are equating the compressive force to the tensile force. So we have Cc, the resultant compressive force in concrete on one hand, and the tensile force on the other hand. 0.36 FCK into B into XU is equal to 0.87 into Fy into AST. Okay, so I'll take a different color, right? So we have we can just cancel out the value of the D. So XU is nothing but 0.87 and Fy is 500 into AST is 1256.64 divided by 0.36 into FCK is 30 into 250. So that gives us a value of 202.46 mm. So if you just consider the aspect of the force equilibrium, so this is the value that we get. Okay, so just considering the force equilibrium, this is the depth of neutral axis that we get, right? And the correct answer is option C. Okay, so we are not considering the limiting depth, which we will be considering the next question. So for the beam that is given in question 6, what is the limiting depth of the neutral axis, and what should be the depth that is considered to determine the moment of resistance of the cross section? Okay, kindly take 30 seconds to 1 minute.
inside F.
Okay, okay. Thank you for the response. So the correct answer for this question is option E actually. Okay, so we're going to look at the solution. So we saw that, you know, for the reinforced concrete beam, we have this, you know, limiting value of the neutral axis depth, okay, that is xu max by d. Xu max by d, essentially, you know, when you plug the value of Fy, we get you know, the for Fy 500 grade steel, this is the, you know, limiting value of xu by d, xu max by d. So essentially this xu max is equal to 0.456 into 400. So 400 is the you know, the value of d, because the overall depth for our question, d is equal to 450 mm, right? So when you consider the cover, so cover is equal to 30 mm for moderate exposure, and additional 10 mm for the stirrups, and we are considering 4 bars of 20 mm diameter, so 20 divided by 2, so that gives us a value of 50 mm. So the effective depth, that is d, is equal to 400 mm, right? So when you multiply this, we get a value of 182.4 mm. So this is the limiting value of the neutral axis depth. So even though, you know, when we equate these two forces, you know, the compressive force to the tensile force, even though we get the depth of neutral axis as, you know, 202.46 mm. So let me just, you know, calculate that for you, what percentage that would be with respect to the neutral axis depth. So that will give us a value of 0.506 mm, sorry, 0.506 times the effective depth. So we should not consider, you know, this value. In order to perform our analysis and design, we need to limit the depth of the neutral axis. So both the value of limiting depth and the depth that should be considered for determining the moment of resistance, right? So both of them needs to be 0.456 times d, which is 182.4 mm. Okay, right. Only, you know, when we consider this xu max by d, so only then we can provide an under reinforced cross section. Okay, so if we consider a value of xu that is greater than you know, xu max by d, sorry, xu max, we will be designing an over reinforced cross section. Okay, we want to avoid that. Okay, so which is why this is the limiting value of the neutral axis depth. Okay, moving on. For the beam given in question 6, what would be the ultimate moment of resistance and curvature as per IS 456 2000? Kindly take 1 minute, you know. So the hint to this question is, we have the formula in Annex 6 of IS 456. So if you don't have, you know, I would recommend that you download the PDF of IS 456 and plug the value and obtain the value of ultimate moment of resistance and curvature.
Answer D.
Okay, thank you for the response. We will wait for another 30 seconds, if the other participants wants to confirm the answer, or if they have a different answer, and after 30 seconds we can go with the right answer and the solution. Yes, so as the participant said, option D is absolutely right. And again, we have this in question 6. We have this the geometric details of the reinforced concrete beam, and as per the annex 6, I will choose a different color. Yeah, so as per the annex G of IS 456, right? So what we need here is the ultimate moment of resistance, that is mu limit. So we are determining the ultimate moment of resistance here, because the calculated the xu calculated is greater than xu by d is greater than xu max divided by d, right? So we need to use this mu limiting value. But if the xu by d is lesser than xu max by d, so it means that the area of steel is the lesser than that for a balanced section, in which case we need to use another expression that we'll be seeing later on, that is 0.87 into Fy ASTD, that value. But this 0.87 Fy ASTD into 1 minus AST Fy by BD FCK. So we need to use that one when XU by D, this is equal to mu. Okay, so I'm just going to separate this. So we are going to use this when XU by D is less than XU max by D. So here in our case XU is greater than XU max by D, so we need to determine the limiting moment of resistance, that is 0.36 XU max by D into 1 minus 0.42 XU max by D into BD square into FCK. Okay, so when we plug the values, that is 0.36 into, we'll simplify it into two decimal places, 0.46 into 1 minus 0.42 into 0.46 into B is 250 and D is 400 square into FCK is 30, the characteristic strength. We get a value of, I got a value of 160.33 kilonewton meter, that is the ultimate moment of resistance, and we need to find out the curvature. So the curvature, ultimate curvature is epsilon c divided by x, so that we obtain by 0.0035, and the x value, as I was mentioning earlier, we need to consider the limiting depth, that is 182.4, sorry, for which I got a value of 19.02 into 10 to the power minus 6 per millimeter, right? Yes, so option D is the right answer. Okay, so we will move on to our next question. So for the beam that is given in question 6, what would be the ultimate moment of resistance and curvature considering the actual material properties? Okay, so in the previous example we looked into the stress block parameters corresponding to the IS code, but here we need to consider the rectangular stress block parameters of concrete. Okay, we have solved a similar question I think in the live interaction session 5, so I request you to solve the problem and let me know the answer.
Answer B.
I'm sorry, is it B for Bangalore or D for Delhi?
Bangalore.
Okay, thank you for the response. We will wait another 30 seconds. Yeah. If the other participant participants want to answer the question. Okay, so option B is absolutely right, and we have in fact we have solved this very same problem in the live interaction session 5 also. So I would like to solve this using the Excel spreadsheets, right, as we did sorry. Yes, I think we can solve using this spreadsheet. I hope that my Excel sheet is visible.
Yes, sir.
Yeah, so we can start entering the values. B is 250 mm and this is 450, 450. Then the effective depth is 400 mm, right? Area of stair is 1256.64, and the compression steel is 0. We are dealing with singly reinforced section. D dash is not relevant for this problem, and the characteristic strength we will consider F prime C has 30, right, and Fy is 500, and we don't have any actual force acting on the beam for this problem. We have we need to find out the ultimate moment. So epsilon c is 0.0035. Now we'll just compare what is the compressive force. So automatically when you put the value of compression steel as 0, the resultant compressive force becomes 0. So we have the resultant stress in concrete as 1406 and tension, the tensile force in steel as 488. So we need to reduce the depth of the neutral axis. So let us see what happens when we put 150. Still the value of Cc is high. Let us try for 140. So still the value of Cc is high, and let me just 135, no, 130, okay, 125, okay, 120, okay, 115. Yes, so approximately I think for value of, let me try 114.8, 114.9. Yes, I think for a value of 114.9, we are able to achieve equilibrium between the compressive force within the concrete and the tensile force in the reinforcing steel, and correspondingly we have the moment of resistance as 218.8 and the ultimate curvature as 30.5. So let us look at the options now. Yes, we have the moment of resistance as 218.7 and 30.5 into 10 to the power minus 6 per millimeter as the curvature. So option B is the right answer. Okay, so we'll proceed to the next question, right? So consider a beam that is having a width of 300 mm and overall depth of 500 mm, and the concrete has a characteristic strength of 40 MPa. Now if the beam is subjected to a design moment of 250 kilonewton meter, so we need to decide whether it will be designed as a singly reinforced beam or a doubly reinforced beam. Okay, kindly take 1 to 2 minutes to answer this question. And these are some of the assumptions that we need to consider. Grade of steel is yield strength is 500 MPa, and we need to consider 10 mm stirrups and moderate exposure environmental conditions.
Answer A.
Okay, thank you for the response. We will wait for 30 seconds for the other participants to answer. Okay, so I'd like to take the question back to the participants. So the participant who answered option A, so can you kindly share with us how you got that answer?
I calculate the limiting moment
Yeah.
mu max. So I obtained it 322, and
Yeah.
as the beam is subjected to moment 250, it's less than mu.
Yeah.
So its singly reinforced section is okay.
Yes, yes. Yeah, so that is absolutely the right approach, and yeah, thanks for sharing with us. And yes, so option is absolutely right. And what we need to do here is whenever this mu limit, we will take up this problem, we will take up this numerical. So when we obtain, we will find out the value of limiting moment of resistance, that is mu lim. So whenever the mu lim is lesser than if mu is lesser than mu lim, we can simply provide a singly reinforced cross section. So we can simply provide a singly reinforced cross section, but when mu is greater than, let us put the suffix 1 and 2. So when mu lim is less than mu2, so let's say that in our case we will find out the value. Let us say we get a value of around 325. Okay, so but if the demand is greater than, let's say if the demand is 500 kilonewton meter, so in that case we need to design it as a doubly reinforced cross section, right? So we are going to find out the value of mu limit in order to arrive at our answer. So mu limit, as we were seeing earlier, that is equal to 0.36 xu max by d, xu max by d into 1 minus 0.42 xu max by d into bd square into fck, right? So we have mu lim, it is equal to let me use a different color for better contrast and visibility, right? We just plug the values 0.36, and for fy is equal to 500, we have 0.46. So this we need to be very careful. We need to plug the value depending on the value of fy, right, into 1 minus 0.42 into 0.46 into b is 300, and effective depth is 450 square into fck is 40. So we get a value of mu limit is equal to how much? It is 324.7 kilonewton meter. So what is our the demand? So we need to design the beam for a design bending moment of 250 kilonewton meter, right? So this is the design bending moment. So since the mu is lesser than mu limit, we can design the beam as a singly reinforced cross section. Okay, we can design it as a singly reinforced cross section. Okay, so we are going to be designing in the subsequent parts of the question, right? So option A is the right answer. So as we have seen in the summary, we have seen two methods in order to determine the area of steel reinforcement. So in this question, I request you to determine the area of reinforcing steel by the method 1, that is by calculating the depth of neutral axis. Okay, kindly take 1 to 2 minutes and suggest the correct answer. So the geometric properties, that is the breadth and the width and the depth of the cross section, it is same as question 10.
Answer D.
Okay, yeah, thank you for the response. Okay, I would suggest to check the calculations once again. Okay, can I go ahead with the correct answer? I would suggest that you take another 30 seconds to verify the calculations, the steps. Then we can have a look at the solution. Okay, I think we can go ahead with the answer. The correct answer is option C. So I would like to show you the calculations for this particular problem. So here we have, as we mentioned earlier, we have two methods. So firstly we will look at the method number 1. So here we need to start as sir was explaining in the lecture, it is a three-step process in order to design the cross section, right? So first we need to find out the value of r. R is mu by bd square. Okay, that is mu is 250 into 10 to the power 6 by 300 into 450 square. So for which we get a value of 4.115. Okay, we have this. Then we go to the second step, that is xu by d. So we are finding the value of neutral axis indirectly, that is 1.2 multiplied by 1 minus square root of 1 minus 4.6 r by fck. Right, so when we plug the values of r as 4.115 and fck as 40, I got a value of 0.329. right? Ultimately in the third step we have AST is equal to mu divided by 0.87 fy into d into 1 minus 0.42 xu by d. It has to be xu, right? So I will just write it down. 250 into 10 to the power 6 divided by 0.87 into 500 into D. So what is D? D is 450 into 1 minus 0.42 into 0.46. Okay, for which I got a value of, I'd like to request the participants to verify if they are also getting the same answer, 96 mm square. Okay, so is there any concern or doubts regarding this? So I got a value of 1481.96 and option C is the right answer. Okay, so if there are no doubts, I think we can proceed to the next question. So for the same beam and for the same moment demand, so I in the question we need to find out the area of steel required using the direct calculation method. So I request the participants to take 1 minute and come up with the right answer. Hello. I hope that the participants are trying to solve the problem. Can I go ahead with the answer?
Yes, sir.
Okay, right. So the correct answer is option D. So yeah, let me just give you the procedure so that we can later you can fire, you can see for yourself. You can verify the calculations, right? So as I was explaining in the method one, it was a 3-step process. Okay, and we obtained a value of 1481.96 mm square. And this particular problem in the method 2, it essentially involves only 2 steps. That is, we need to find out the value of R, and we have seen that in the previous. Let me use a different color for contrast. So we know from question 11 that the value of R is equal to 4.115, right? 4.115. Now we need to find out the value of PT, right? That is the percentage of steel reinforcement in the tension, that is PT by 100 is equal to, I'm going to just substitute the values using this equation directly. FCK is 40, right? 2 into 500, right? into 1 minus under root 1 minus 4.6 into 4.115 divided by FCK is 40, which gives us a value of, can anybody help me? Okay, anybody?
0.0109.
Okay, so let me write the answer and you can just tell me whether you are getting the same. I got a value of 1.097. Okay, just be careful as to what all terms we are considering within the square root. I request the participants to kindly check, and yeah, I'll use a different color now. Okay, so when we just plug the values once again, PT is 1.097 is equal to AST by B into small d. B is 300 by 450 into 100, right? So when we simplify this, we get a value of AST as 1480.8 mm square, right? So when we calculate the AST by method 1 and method 2, so it has to match. I mean, though it might not match to the final digit, but still it will be more or less comparable. So 1480.8, that is option D, is the correct answer as per my calculations. So the participants, those who are attending the session and those who are watching the YouTube video, you can just verify. Yeah, so here also we got a value of 1481, and in method 1 1481.96, and here also we are getting almost similar value 1480. Okay, so I request you to just do this, and yeah, if you do this you'll be able to very easily solve the assignment questions. Okay, that's the purpose of this. Yeah, so we are done with the topic of singly reinforced beam. Now we have a conceptual question for the doubly reinforced cross section. Which among the following is not a reason for providing compression reinforcement in the flexural members? So kindly read the options, take 30 seconds, and let me know what is the correct answer.
Answer E.
Yeah, thank you for the response. Anybody else would like to participate and confirm the answer, or if you have any other answer? Okay, so I think we can go ahead, and option E is the right answer. So we have looked into the various reasons why the compression steel is preferred. So usually, even if the beam is reinforced, is designed as a singly reinforced beam, we provide this nominal reinforcement in the compression region. Let me use a different color again. So we provide nominal reinforcement in the compression zone so that it is able to support the stirrups. Okay, so these are also called as hanger bars. It can be of very nominal diameter, let us say 2 of 12 mm diameter. So they not only help us in providing the stirrups, but they also though the beam is designed as a singly reinforced cross section, they definitely come into play whenever the beam goes into flexure, and they also resist a part of the flexural loads. Okay, so these are some of the reasons for providing the compression steel. Whenever the capacity is less for a singly reinforced cross section, we provide the compression reinforcement, making it a doubly reinforced section. Secondly, in order to transfer the loads to compression steel, we provide the doubly reinforced, and again as we can see, you can refer to the slides, but option E is the incorrect answer, because we want the beam to fail in a tension controlled manner, and compression steel actually does the opposite. Instead of allowing for a compression failure, because the compression steel takes up the compressive forces, it reduces the stress acting on the concrete in the compression zone, as a result of which it changes the failure mode from compression governed to tension governed failure mode. Okay. Yeah, so this is the correct statement. So option E is the wrong statement, and hence it is the correct answer. Okay, moving on. So we have the numericals. So we will consider the same beam which we have considered previously, having a width of 300 mm and overall depth of 500 mm, and it has a characteristic strength of 40 MPa. If the beam is subjected to a moment of 600 kilonewton meter, what is the area of steel required in the compression zone? Okay, so kindly take 2 minutes and come up with the answer. Okay, so we need to find out the area of steel in the compression zone, that is ASC. Okay, please take 2 minutes. Okay, then we can have a look at the correct answer and the solution. So 1 minute is remaining for the participants if you want to answer. Or if you want some time, you can, there is no hurry.
Answer E.
Okay, thank you for the response. Yes, so I think we can look at the correct answer. So it is rather, it is option B, or is it? I think it is option D, I think. So we can just check. So we can solve the problem and we can see. No? Okay, so we have the design bending moment, that is mu. Mu is 600 kilonewton meter, which is actually greater than the value of mu limit, right? So it has to be designed as a doubly reinforced cross section. Okay, so first let us plot the strain distribution along the depth of the cross section, because we are going to be needing it at a later stage. Okay, so this would be the value of xu. Okay, and we will consider, if this is epsilon c, that is strain in concrete, we have epsilon sc. Okay, so we will go step by step in this problem. So since it is a doubly reinforced cross section, we are going to limit the depth of neutral axis at 0.46 times d. So what would be the value of xu? 0.46 into 450. So what would this value be? Can anybody confirm?
$207.
Okay. Yeah, thank you. So the xu would be 207 mm. Okay, so this would be the, and we need to obtain this value of epsilon sc for our calculations. I'll be showing you later. So let us calculate that from the similar triangles. Epsilon c divided by xu is equal to epsilon sc divided by xu minus d prime. I hope that it is clear, this particular concept is clear. So here we have epsilon sc is equal to epsilon c by xu into xu minus d prime, that is 0.0035 by 207 into I'm just going to write it directly. Xu minus d is 157. So what would this value be? Epsilon sc
0.00265.
Okay, okay, we have 0.00265. Thank you for the answer. Now we have mu minus mu lim is equal to fsc into asc into d minus d prime. I hope we are clear. We are clear on this equation. I hope we are clear.
Yes, sir.
Yeah. So we have mu as 600, right? Yeah. We have 600 minus, and we saw that it is 324 point, how much mu limit is? Yes, 0.66. Okay, into 10 to the power 6 is equal to FSE. So why I calculated the value of epsilon SE is because we need to find out the value of plug the value of FSE, so that here in this equation ASE is the unknown and we need to find out the value of ASE, right? So when you look at this table, so I request all the participants to have a look at this. This table is not only provided in the notes, but also it is in the SP6 1980 page 6, and for a value of 0.00265 we can obtain the value of FSC from the linear interpolation. So when you interpolate between these two values of stresses, 391 and 413, corresponding to a strain of 0.00265, I obtained a value of 407.9. okay, so you can just compare that later on. Okay, I obtained a value of 407.9, which is between these two values, 391 and 413, into ASC. Again, I need to continue in the next line, sorry about that. And we have D is 450 minus D prime is 50. So when we simplify, so may I know what is the answer of ASC?
$1,700.
Yeah, I mean, if you do it carefully, it would be 1687.5. Right, I hope we are getting the same answer. So 1687.5, or rather 6. So it has to be option D. Okay, option D is the right answer. So yeah, since we were having this doubt, I wanted to solve it from the scratch. So option D is the right answer. I hope that we are clear about the solution, right? Yeah, so so option D is the right answer. Okay, so this is the area of compression steel that is required. So again, with the permission of participants, we have already crossed 9 o'clock as usual, so I'll be taking another 10 minutes.
Okay, sir.
Yeah, so yeah, please yeah, so we will continue with the problem. We have another 3 questions to go in today's session. It is all numerical based. So for the same question, what is the area of steel required in the tension zone? Okay, so the hint is here is that we need to calculate the area of steel you may start solving the problem. So here the area of steel consists of 2 parts, that is AST1 and AST2. So this is corresponding to the limiting area of steel, that is AST lim, corresponding to a limiting the ultimate moment of resistance of a singly reinforced cross section, and this has to balance the area of steel in the compression region. Okay, so this is the hint I would like to provide before starting the solution. So I would request the participants to take 1 or 2 minutes to solve, and if you require additional time, kindly let me know. We will go as per your pace.
Answer E.
Okay, thank you for the response. Okay, so I think we can go ahead with the solution, because since we are already running out of time, and my suggestion to the participant is that I know that the options are closely spaced, but we need to have some accuracy. So that is my humble suggestion. Because as engineers we need to be economical, we need to optimize the design. So the correct option was option C. So we will look into the solution now. So as I was mentioning earlier, it consists of two parts. So first we will calculate for the AST limb. Okay, then we can calculate the area for. So we have the limiting for the ultimate moment of resistance of singly reinforced cross section. AST limb is given by PT limb by 100 into Fy by Fck is equal to 0.189. Okay, this is corresponding to Fy is equal to 500 MPa. So I hope you remember this particular expression. I can go back to the notes and just highlight it very quickly. Yes, so we have the PT limb for 500. We have PT limb by 100 into Fy by Fck is equal to 0.189, right? So when we substitute value of Fy as 500 and Fck as 40, okay, we get the value of PT limb as okay, I think it is 1.512. Am I right? Yeah, we get a value of 1.512. Okay, so the AST corresponding to this would be PT limb is equal to AST by BD into 100. So we get AST1 is equal to 2041.2 mm square, right? And this is corresponding to a limiting moment of resistance. Then we find out AST2 by this particular equation, FSC into AAC by 0.87 Fy. Now by plugging the values of FSC, AAC from the previously obtained values, we get AST2 is equal to 1582.42 mm square, right? So AST is nothing but the summation of AST1 and AST2. So we obtain the value of AST as 3623.62 mm square. Okay, I request the participants to calculate and check whether they are also getting this value. So option C is the right answer. So yeah, so I request the participants to solve this problem, right? So earlier we looked at the design problem. Now it is an analysis problem. So for an RC beam of the same dimensions, right, the concrete has the same characteristic strength of 40 MPa. The beam is reinforced with 6% steel and 3% steel of the gross cross-sectional area in the tension zone and the compression zone respectively, and it is having an effective cover of 50 mm. So what would be the ultimate moment of resistance and curvature as per the IS code? Okay, so I request the participants to take 1 minute, then we can have a look at the answer. So the process of arriving at the results from the analysis is a bit more involved and iterative when compared to the design procedure. So can we proceed with the answer?
Okay, sir.
Okay, no, we can, if you are still trying, actually we can take another few minutes.
Yes, sir, you may proceed.
Okay, okay, yeah, so it is a bit involved, actually the calculations. It is the procedure for the analysis of doubly reinforced cross section. It is little more complicated when compared to the design. Okay, because here we need to the change the value of x and achieve the force equilibrium. So again here I will just outline the procedure. The correct answer is option A. I will just outline the procedure here only, so that we can we can check it later on, and if there is any doubt later on, I'll be happy to take it up in the next session. So here step 1 is assume the value of x. We are going to be solving this using the Excel sheet, but if you want the hand calculation, we can take it up next time. Assume the value of x. Then we need to find out the value of epsilon sc and epsilon st. Okay, then we need to check the value of cc plus cs, compression in the concrete zone, compression in the compressive steel. Then we need to equate it with the force in the tension reinforcement, and if that is satisfied, okay, So if it is yes, again we have an if loop over here, and if it is no, we have to go back to this procedure. If it is no, again we need to change the value of x, and once this condition is satisfied, we need to find out the value of mu and xu. Okay, I'm sorry, we need to find out the value of mu and the curvature. Right, mu and curvature. So we will solve it using the spreadsheet, and if there is any doubt, we can do the hand calculations in the next class. Okay, let me go back to the spreadsheet now. Yeah, so we are looking at the calculations as per the IS code. So we have width of the beam is 300 mm, and the depth is 500, and I have entered the value of the AST corresponding to 6% of the reinforcement. That comes out to be 9000 mm square, and the compression steel is 3%, that is 4500 mm square. D prime, that is the effective cover for the compression steel, is 50 mm. Then the characteristic strength is 40 mm. Then Fy is 500 MPa, and so this is already calculated. Like as I was telling earlier, we need to establish the equilibrium between the compressive forces and the tensile forces, and for a value of x that is 298.3 mm, we obtain Cc plus Cs is equal to 3167 and 3167. So here, those who have been following the class very carefully, the value of x is greater than the limiting depth for compared to the neutral axis. That is, it is greater than 0.46 times the effective depth. But this is the limiting depth is valid only for the balance section, but for the analysis sake, I mean, it is valid only for the singly reinforced section. But for a doubly reinforced section, for the purpose of the analysis, we can consider a value of neutral axis depth that is greater than 0.46 times the effective depth. So after this we find out the moment of resistance by multiplying the compressive or the tensile force with the lever arm. So we get a value of 1166.9 kilonewton, and the curvature is 11.7 into 10 to the power minus 6. 1166.9, yes, 1166.9 and 11.7 into 10 to the power minus 6. So option A is the right answer. So if you have any question, we can solve it using the hand calculation in the next class. And we have the last question for the day. So what would be the ultimate moment of resistance and curvature considering the actual material properties? So if you allow me, I'll go straight ahead to the solution, because we have already overshot the time limit.
Okay, sir.
Yeah. So we will just go to the spreadsheet once again. So yes, so this was as per the IS code, and this would be considering the material properties. So we have B is equal to 300, D is equal to 500, and this would be 450, and this would be AST would be 9000, and AC would be 4500. D prime F prime C. Yes, so for x value of 257.15, okay, let's see what happens. Okay, I think this is the wrong sheet. I think let me go here. Yeah, let me check it once again. 300, 500, 450, 9000, 4500. Yes, and for x value of 257.15.
Two 31.9.
Yeah. Okay. 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 I think. For 231.9, is it?
Yes, sir.
Okay. I need to check this value actually. Okay, so we need to reduce it slightly now to 73.8. Okay, we need to increase. No, I think we need to further reduce to 73.6. Increase it to 73.7. Oh, okay. I think okay, so 273.95. So I think we need to reduce this a little bit, 0.3. Okay, so I think we can consider this approximately. Okay, so I will just confirm this value. But when I did the calculations yesterday, I was getting this value, but oh, I see the problem here. I should have taken the value of f prime c as 40 MPa. So if you consider the f prime c as 40 MPa, you can substitute the value of x as 257.15, right? So we will get, I hope it is clear now to the participants.
Yes, sir.
Yeah. So this was the issue. So after plugging the value of f prime c as 40 MPa for x value of 257.15, I was able to achieve equilibrium between the tensile forces and the compressive forces, and the corresponding value of m and phi would be 1652 and 13.6. Okay, so the correct answer is option D, right? So yeah, I think we have come to the end of this session. So keep the annotations, and yeah, thank you one and all, for being in the session. So yeah, thank you for your patience and for your time, and we will meet next week, same time, for the design for shear. Okay, on that note, if there is no further comments, I would like to end the session.
Thank you so much, sir.
Yeah, thank you so much. Good night.
Good night, sir.